Hello friends, how are you? In our last classes, we were discussing about IUPAC nomenclature of hydrocarbons. We discussed about IUPAC nomenclature of hydrocarbons. Okay, I hope you understand that and also completed the given work. Okay. Now, after discussing the nomenclature of alkane, alkene, and alkyne, I am starting a new topic, that is allotrope of carbon. That is allotrope of carbon. The first question that comes in our mind, that is, what is allotrope? What is allotrope? The simple definition is the two or more pure forms. Allotropes are pure form of any element. Before discussing the definition, we discuss about some facts or some points of that. It is purest form of any element which have same chemical properties, but different in physical properties. For example, the diamond and graphite both are the allotrope of carbon. That means they have same properties, same chemical properties, because both of them made up by pure carbon. But if we consider the physical appearance or physical properties, is they are same? No. Diamond, which is the hardest natural substance, while the graphite, that is soft. Diamond, that is bad conductor of heat and electricity, while graphite, that is a good conductor of heat and electricity. That means they have quite difference in physical properties, but the chemical compositions and the chemical properties are same. Got it? That is known as allotropism. Okay. Now, if we consider simple words, then we can say that the purest form of any elements which have similar chemical properties but difference in physical properties or physical modifications are called allotropes. Got it? So we can say that two or more pure form of an element which are same in chemical properties but have difference in physical properties are called allotrope of that element, and this property is called allotropism or allotropy. Got it? Or in simple word, we can say that the physical modifications of pure form of an element which are same in chemical properties, called allotrope of that element. Here, physical modification, that means they have different in physical properties. Got it? So the physical modifications of a pure form of element which are same in chemical properties are called allotrope of that element. Got it? Now, if we consider the allotrope of carbon, then it is mainly grouped into two categories. One is crystalline allotrope and second is non-crystalline allotrope. The question comes in our mind, that is, what is the crystalline and what is the non-crystalline or amorphous? When the particles are arranged in the definite geometry with definite bond angles, then it is called crystalline. And if that is absent, then it is called non-crystalline or amorphous. Got it? Understand? Now, the diamond grouped into two categories. One is crystalline allotropes and second is non-crystalline allotropes. Got it? Crystalline allotropes further divide into three categories. One is diamond, second is graphite, and third is fullerenes. Got it? And non-crystalline or amorphous allotropes further divide into various categories, that is like the coal, coke, wood charcoal, animal charcoal, lamp black, gas carbon, etc. Out of these, the graphite, fullerene and diamond, these three allotropes are in our syllabus. These are in our syllabus. Got it? That means crystalline allotropes are in our syllabus. Got it? Now, let's start to discuss about that. As I already told you the definition of crystalline forms. So again here repeat that. The allotrope. So if we use that term in our dev term, that is crystalline allotrope, then we can say that the allotropes of carbon in which its atoms are arranged in definite geometry. That means here the geometry is definite and with definite bond angle are called crystalline allotrope of carbon. These are called crystalline allotrope of carbon. Got it? Now let's discuss about the first one, that is diamond. To understand this theory, we have to consider its structural diagram first. Firstly, we have to discuss about its structural diagram. One thing, let me clear you, the making of the crystalline diagram of diamond is a difficult task. I hear this diagram is different from your book's diagram. As per me, that is much easier, because in that we are also showing the tetrahedral structure, and here we are also showing in the tetrahedral structure. So that is the similar point about that. You have to draw this one, and for that you have to draw hexagons. Firstly, you have to draw hexagons. Got it? And after that, one point here, one point here, that one point here, that one point here. That means where the lines are joining in the upper side, draw a line towards the downward, and where the lines are joining to downward, put a line in upward direction, like this. Here, like this. Got it? And here they are joining upper side, so their line is downside. And after that, join all of them. So in that way you get a little bit three-dimensional diagram. Okay, here if we consider each carbon atom, suppose I am considering this carbon atom, then this carbon atom is attached with the four other carbon atoms. That one carbon here, one carbon here, one carbon here, and one carbon here. That means in diamond, each carbon atom is bonded with four carbon atoms in tetrahedral geometry. In which the bond length, that means the distance between the two carbon atoms, is 154 picometer or 1.54 angstrom. Okay, now clear? Now let me discuss its theory about it. It is the pure form of carbon. Diamond, it is a pure form of carbon in which each carbon atom is strongly bonded with four other carbon atoms in three-dimensional tetrahedral geometry. In diamond, that is a pure form of carbon. It is the pure form of carbon in which each carbon atom, as we discussed in the diagram, that each carbon atom is strongly bonded with four other carbon atoms. Each carbon atom is bonded with four other carbon atoms in the three-dimensional tetrahedral geometry. The geometry was that one. The geometry was tetrahedral. Each carbon atom is bonded with four other carbon atoms. Each one is bonded with four other carbon atoms in tetrahedral geometry. Got it? The bond distance between the carbon atoms is 1.54 angstrom or 1.54 angstrom or 154 picometer. Got it? Now, let me consider its some properties, that why it is bad conductor and why it is hardest natural substance. Got it? Since here the tetravalence, that means four valencies of carbon are satisfied. That means carbon is bonded with four other carbon atoms completely. That means satisfied. Therefore, diamond is a bad conductor. Therefore, diamond is a bad conductor. Got it? Clear? Since the four valencies of carbon are satisfied, therefore diamond is bad conductor. Now the second thing is why it is so hard. It is because of the three-dimensional network, that is tetrahedral. Tetrahedral three-dimensional network of strong covalent bonds. Strong covalent bonds. In the diamond, there is the three-dimensional tetrahedral network of strong covalent bond, as we discussed. Okay, that's why diamond is hardest natural substance. It is hardest natural substance and its melting point is very high. It is 3843 Kelvin. It is very high. Okay, now our last topic is how the diamond is formed. Naturally, diamond is formed by the pressure of the rocks on the layer of the coal. Coal, that means carbon. Coal, that means carbon. Okay, when the pressure of earth crust, exerted on the layers of the coal, then the carbon particles, comes closer. The carbon particles comes closer and make the tetrahedral transparent network. That means diamond. Got it? So because of the earth pressure of the earth crust, the coal converted into diamond. Artificially, it is synthesized by pure carbon at very high temperature and pressure. It can also synthesized or also prepared artificially in the factories. Got it? For that, it's the pure carbon at very high temperature and pressure when treated, then artificial diamond is obtained. Got it? But one thing, let me clear you, the artificial diamond is smaller in size as compared to the natural diamond, because the earth crust pressure, that is much higher than the pressure which we can create in our labs or in our factories. Got it? Now, after discussing the diamond, we have to also discuss about the uses of diamond. First, it is making jewelry. It used in making jewelry, as you know that diamond, that is used in making the ornaments. Second, used in glass cutters. The glass cutter, the pencil like the substance glass cutter, as you know that, I think you have seen, there is a metal pencil like structure which used to cut the glass. At the end of that, a rough diamond is placed. Okay, So that means we can say that use in glass cutter. Third, use in machines for cutting rock and stones. The machines which used to cut the rocks, like the marble rocks into small pieces, or we can say the tiles. The machines which we use have belt of rough diamond. There is a belt of rough diamond which cut the huge stones into small pieces. Got it? Fourth, use in making phonograph needle. Phonogram needle. Phonogram, in the pictures you have seen, there is a black color disc which is rotating, and there is a speaker or mouth like a structure which is placed above, and there is a needle. When we put that touch there is a song is playing. That is the phonogram. Okay, so that is the phonogram needle. To draw that needle, to make that needle, diamond is used. Okay, now let we discuss the graphite. Now let we discuss about the graphite. Graphite is a black colored opaque shiny allotrope of carbon. That is graphite, which is in our pencil. This black colored substance, this one, that is graphite. So it is black colored opaque shiny allotrope of carbon. Was one thing that come in our mind, that why it is called graphite. It derived from the word grapho. Which means write, or to writing. And you know that graphite is used for writing. That's why it is called, and from there it get the name graphite. Now if we consider the structure, in graphite each carbon atom is bonded with three other carbon atoms. Each carbon atom is bonded with three other carbon atoms in the hexagonal rings. Got it? Each carbon atom is bonded with three other carbon atoms in the hexagonal rings. To satisfy the valencies, out of these three, one bond is double bond. But here we cannot identify that, we cannot show that, because this double bond is continuously, that is delocalized. It is delocalized. That means it rotates from the one part to second part of the ring. The delocalized bonding you will read in higher classes. So here delocalized double bond is found, which used to stabilize the molecule, or we can say that to fulfill the valency of carbon. Got it? So one carbon is bonded with three other carbon atoms in the hexagonal plane, or hexagonal rings. In these three bonds, one bond is double bond, one bond is delocalized double bond, to satisfy the tetravalency of carbon. Okay, these two-dimensional hexagonal sheets of graphite arrange on each other. This is the, for example, this is the first layer, and that is second layer. If we consider, then more layers are there. So that is the one layer, and that is another layer, like this. That is one layer, and that is second layer. Got it? So these layers are arranged on each other, and they are bonded with weak van der Waals forces. That is weak van der Waals forces. Because of that, the layers are arranged on each other. Got it? But as you know that the van der Waals forces are weak, and here the space is large enough, because if we compare that, here in the graphite, the carbon particles of one layer are at 144.5 picometer distance, but the carbon particles of different layers are large enough, that is 344 picometer. So because of the weak attraction forces and larger distances, these sheets of graphite slide over each other. These slides slip slide or slip on each other. Because of that, the graphite becomes smooth and slippery substance. Because of that, the graphite is smooth and slippery substance. Got it? Clear? Suppose that is these are the layers. If I push this layer, then because of the weak forces, this layer can easily move from that place. Got it? So there is weak forces and larger distance, the layers slide on each other, and because of that the graphite becomes smooth and slippery substance. And because of that, this nature, graphite is used as dry lubricant. It is used as dry lubricant. Got it? Lubricant, that means which is used to reduce the friction. Okay, now since there out of four valencies, three is satisfied here, one is delocalized bonding but it is not stable, so only three valencies are satisfied, and one valency, that means one electron is free. Got it? This because of the presence of the free electron, a large space between the layers of graphite. Because of the presence of the free electron and large space between the layers of graphite, it is good conductor of electricity, because that free electron can take place here and can easily conduct the electricity. That's why graphite is a good conductor of heat and electricity. Got it? Now for making, firstly, this diagram, it is very easier, but one thing that you have to mind it, that is you have to make tilt hexagons. That is tilt hexagon. Why? Because this point is not here, that is slightly shifted here. Make that line, that line, that line. Now this line will be equal to that, this line is equal to that, and that line equal to that. So that kind of lines when you use, then the diagram becomes tilt. This tilt diagram give you a 3D impression. Got it? So that's why we can use this tilt impression to show the 3D diagram of graphite. Now let me read its theory about it. It is black colored opaque shiny allotrope of carbon, as we discussed. It named derived from the word grapho, which means writing. As you know that graphite is used in writing. In graphite, each carbon atom is bonded with the three other carbon atoms. In the graphite, each carbon is bonded with three other carbon atoms in hexagonal ring structures. In these bonds, one bond is double bond to satisfy the tetravalency of carbon. Got it? The two-dimensional hexagonal sheets of the graphite are arranged on each other. The layers, as we discussed, that the layers, two-dimensional layers, are arranged on each other. Got it? And due to weak attraction forces and more distance between layers, the sheets of graphite slide over one another. That means these layers can easily slide on each other. Got it? It makes graphite smooth and slippery substance. Because of that, the graphite is smooth and slippery substance. Hence, graphite is used as dry lubricant. Because of that, it is used as dry lubricant. Now, because of the presence of the free electron and large space between layers, graphite is a good conductor of electricity. It is a good conductor of electricity. Got it? Now we consider its uses. Then first, as you know, that use in pencils. Second, use in dry lubricant. Third, in use in making electrodes because it is a good conductor. Okay. Use in polished iron objects. And last one, use in as moderator in nuclear reactors. As a moderator, it is used to absorb free neutrons and control the nuclear reactions. Got it? Now, our next topic is difference between diamond and graphite. This is an important question. It can ask. They write the difference between diamond and graphite. All of these differences except one we discussed in our lecture section. That means when we discussed about the structure of diamond and structure of graphite. Diamond, that is colorless, transparent, while graphite, that is black colored, opaque. It is colorless, transparent, while the graphite is black colored, opaque object. Second, diamond, it is hardest natural substance. I am saying hardest natural substance, not saying hardest substance. Hardest substance is calcium carbide, but here that is hardest natural substance, and hardest natural substance is diamond. Got it? Graphite, that is soft, smooth and slippery substance. As we compare with the diamond, it is soft, smooth and slippery substance. Got it? Third point, specific density. Specific density or relative density, that means the density compared to the some particular solvent like the water, that is specific density. Its specific density is much higher than graphite. It is 3.51, while the graphite it is 2.25. Okay. Now the fourth, that is high melting and boiling point. As we discussed that diamond has high melting and boiling points. Got it? While the graphite has low melting and boiling points. As we compare with the diamond and graphite, graphite has low melting and boiling points. Got it? Diamond, again, that is bad conductor of heat and electricity. As we discussed, why? Because diamond do not have free electrons. It's all the tetravalency. All the tetravalency is satisfied. So diamond do not have any free electron or free valency. That's why it is bad conductor of heat and electricity. Got it? If we consider the graphite, it is good conductor of heat and electricity because graphite have free electron. Graphite have free electron and more space between the layers. That means the two-dimensional layers, there is more space, and because of that the free electrons can easily move through the graphite. And since when the easy motion of the electron or charged particles, then they comes in the category of good conductor. So because of that, graphite is a good conductor of heat and electricity. Got it? Now sixth difference is graphite is tetrahedral structure. As we discussed, in graphite there are tetrahedral structures, while in diamond these are tetrahedral structure, while in the graphite these are hexagonal structures. In the graphite these are hexagonal, while in diamond these are tetrahedral structure. Got it? and there are other differences. You can also derive that it is found, it is in this the particles are much closer, here the particles are loosely bonded, and like lots of like that. But these six are very common differences, out of which any four can be asked by examiner in our paper. Got it? So that is the difference between diamond and graphite. Okay. About the third allotrope of carbon, fullerene, we will discuss in third, because the making of the diagrams, that is much complex structures, that diagram. So I want to discuss one more time again about that. For making the diagram of diamond, you have to draw first these hexagons, okay, then that point, and that where the lines are joining upper side, draw a point below downside, similarly from that this, okay, draw it, and now join them, join all of these particles like this. So you will get tetrahedral structures. Here again this is structure. If you consider this, then it is inverted, but that is same. So that is structures. And in graphite you have to draw hexagons, but there is tilt hexagons, so that the particles can easily shown that from where, on which particle it is attached. Got it? About the structure of fullerenes we will discuss in next class. Thank you.